Standard Model 1978 to question mark. In the current view, then all matter is made out of three kinds of elementary particles: leptons, quarks and mediators. There are 6 leptons classified according to their charge Q, electron number Le, muon number L mu and tau number L tau. They fall naturally into 3 families or generations. Lepton classification. First generation: electron Q-1, Le1, L mu 0, L tau 0. Electron neutrino Q0, Le1, L mu 0, L tau 0. Second generation: mu Q-1, Le0, L mu 1, L tau 0. Muon neutrino Q0, Le0, L mu 1, L tau 0. Third generation: tau Q-1, Le0, L mu 0, L tau 1. Tau neutrino Q0, Le0, L mu 0, L tau 1. There are also 6 antileptons with all the signs reversed. The positron, for example, carries a charge of +1 and an electron number -1. So there are really 12 leptons all told. Similarly, there are 6 flavors of quarks which are classified according to charge, strangeness S, charm C, beauty B and truth T. For consistency, I suppose we should include upness U and downness D. Although these terms are seldom used, they are redundant in as much as the only quark with S equals C equal B equal T equals 0 and Q equal 2/3, for instance, is the up quark. So it is not necessary to specify U equal 1 and D equal 0 as well. The quarks too fall into 3 generations. Quark classification. First generation: down quark Q-1/3, D-1, U0, S0, C0, B0, T0. Up quark Q2/3, D0, U1, S0, C0, B0, T0. Second generation: strange quark Q-1/3, D0, U0, S-1, C0, B0, T0. Charm quark Q2/3, D0, U0, S0, C1, B0, T0. Third generation: beauty quark Q-1/3, D0, U0, S0, C0, B-1, T0. Truth quark Q2/3, D0, U0, S0, C0, B0, T1. Again, all signs would be reversed on the table of antiquarks. Meanwhile, each quark and antiquark comes in 3 colors, so there are 36 of them in all. Finally, every interaction has its mediators: the photon for the electromagnetic force, 2 W's and a Z for the weak force, the graviton presumably for gravity. But what about the strong force? In Yukawa's original theory 1934, the mediator of strong forces was the pion, but with the discovery of heavy mesons, this simple picture could not stand. Protons and neutrons could now exchange rhos and etas, k's and phi's and all the rest of them. The quark model brought an even more radical revision. For it, protons, neutrons and mesons are complicated composite structures. There is no reason to believe their interaction should be simple. To study the strong force at the fundamental level, one should look rather at the interaction between individual quarks. So the question becomes, what particle is exchanged between 2 quarks in a strong process? This mediator is called the gluon. And in the standard model, there are 8 of them. As we shall see, the gluons themselves carry color and therefore, like the quarks, should not exist as isolated particles. We can hope to detect gluons only within hadrons or in colorless combinations with other gluons, glue balls. Nevertheless, there is substantial indirect experimental evidence for the existence of gluons. The deep inelastic scattering experiments showed that roughly half the momentum of a proton is carried by electrically neutral constituents, presumably gluons. The jet structure characteristic of protons scattering at high energies can be explained in terms of the disintegration of quarks and gluons in flight. And glue balls may conceivably have been observed. But no one would say that the experimental evidence is really compelling at this stage. This is all adding up to an embarrassing large number of supposedly elementary particles. 12 leptons, 36 quarks, 12 mediators. I wouldn't count the graviton since gravity is not included in the standard model. And as we shall see later, the Glashow-Winberg-Salem theory calls for at least one Higgs particle, so we have a minimum of 61 particles to contend with. Informed by our experience first with atoms and later with hadrons, many people have suggested that some at least of these 61 must be composites of more elementary subparticles. See problem 1.17. Such speculations lie beyond the standard model and outside the scope of this book. Personally, I do not think the large number of elementary particles in the standard model is by itself alarming, for they are tightly interrelated. The 8 gluons, for example, are identical except for their colors, and the second and third generations mimic the first. Figure 1.16. Figure 1.15. The 3 generations of quarks and leptons in order of increasing mass. In the next chapter, we shall see how this structure leads to the first systematic and comprehensive theory of elementary particle dynamics. References and notes. Problems.